Today, we tackle a problem where you're given a specific coordinate and a list of other points. The challenge is to find the index of the point that's not only valid based on a simple rule, but also the closest one to your starting position. The problem, find nearest point that has the same x or y coordinate, asks us to find the index of the valid point with the smallest Manhattan distance from our current location, represented by x and y. A point is considered valid if it shares either the same x or the same y coordinate as our current position. If multiple valid points have the same minimum distance, we return the one with the smallest index. If no valid points exist, we return -1. A straightforward but less efficient approach would be a two-pass brute force. First, we iterate through all points, filtering out only the valid ones, those sharing an x or y coordinate with our target. We'd store these valid points along with their calculated Manhattan distances and original indices in a temporary list. After this initial pass, we'd then iterate through our temporary list to find the minimum distance and its corresponding index. This approach uses big O of n time for both passes and big O of n space to store the intermediate list of valid points, which can be inefficient if many points are valid. The key insight for an optimal solution is realizing we don't need to store all valid points. We can find the nearest valid point in a single pass. We'll maintain two variables, one for the minimum distance found so far, initialized to a very large value, and another for the index of the point corresponding to that minimum distance, initialized to -1. As we iterate through each point in the input array, we first check if it's a valid point, meaning its x-coordinate matches our target x, or its y-coordinate matches our target y. If it's valid, we calculate its Manhattan distance. Then, we compare this new distance with our current minimum distance. If the new distance is smaller, we update our minimum distance and store the current point's index. If we find no valid points throughout the entire iteration, our index variable will correctly remain -1. Let's trace this with our example, target point 3, 4, and a list of points. We initialize minimum distance to infinity and minimum index to -1. We start with the first point, 1, 2. It's not valid, so we skip it. Next, point 3, 1. Its x matches our target x of 3, so it's valid. The distance is 3. Since 3 is less than infinity, we update minimum distance to 3 and minimum index to 1. Point 2, 4. Its y matches our target y of 4, so it's valid. Distance is 1. This is less than our current minimum of 3, so we update minimum distance to 1 and minimum index to 2. Point 2, 3 is not valid. Finally, point 4, 4. Its y matches our target y of 4, so it's valid. Distance is 1. This is not strictly less than our current minimum of 1, so we don't update the index, adhering to the smallest index tie-breaking rule. After checking all points, our minimum index remains 2. This is correct because point at index 2, with coordinates 2, 4, is a valid point and has the smallest Manhattan distance of 1 from our target 3, 4. You'll spot this one-pass pattern when the problem asks for a minimum or maximum value based on a condition, especially if it involves iterating through a list. The key is that each item's validity and contribution to the minimum can be determined independently, without needing prior or future context from other items. This optimal approach achieves an big O of n time complexity because we iterate through the points array only once. Space complexity is big O of 1, constant time as we only use a few constant variables. This simple one-pass iteration is a common and efficient pattern. Try the next problem, same pattern. Don't forget to like and subscribe for more DSA insights.